Welcome to the lesson 26 of industrial instrumentations. In this lesson, basically we will cover a nucleonic instrumentation. Let us look at nucleonic instrumentation. Means that we will use some radioactive sources and there will be corresponding detectors, and there are some advantages of this this type of instrumentation, because we have seen that in the lesson 25 we have covered ultrasonic instrumentation. So, there are some typical advantage of the ultrasonic, but there are some cases like if you want to launch that ultrasonic waves in air, it is just impossible, where the radioactive rays can move through air. So, that is a great advantage of this particular instrumentation. So, it is to be covered very extensively. Let us look at the contents of this particular lesson. Contents: principles of nucleonic instrumentation, radioactive sources, radioactive source elements, what are the different elements which will which will make the radioactive sources. Basically radioactive sources means alpha, beta, gamma rays, but what are the elements which will actually used for used in the nucleonic instrumentation that we must study. Its application in industrial instrumentations, that means you will find the label gauge, there is typical applications of the measurements of label, then typical applications of the measurements of the coating of sheets in the rolling mills. So, there are various applications we will find in this particular type of instrumentations, right. So, that we will cover in details, all the different applications we will see. Then detectors, what are the different detectors used in the this type of instrumentation, nucleonic instrumentation. Then also, even though it is a little diverse, we will cover the nuclear medicine, because the nuclear medicine also uses some detectors, okay, some sources, some detectors, which is very similar. So, there is some instrumentation there also. So, we will cover in this under the head of nucleonic instrumentation, we will also cover the nuclear medicine. Right. Now, nucleonic instrumentation looks like this, used for industrial measurement. It is based on radioactive material, so it can travel in air, thus an improvement over ultrasonics which cannot travel in air. We have seen that if you try to launch the air ultrasonic waves in air, it is almost impossible, and we have seen that in the cases like if I want to travel, using these particular principles, we made the level gauges also, because when the ultrasonic waves are traveling through waters, and when it reaches the top surface, it is almost negligible portions will be transmitted in the air, most of the portions will be deflected back from the top surface. So, using that principles, we made the level gauges. We have seen that thing, but this is the disadvantages also, because in many situations we may need to measure the we want to transmit the signals, okay, because all these signals, all this particular method, that means ultrasonic methods or nucleonic instrumentations are non-invasive type of techniques. Okay. So, in some cases if I want to launch these rays through the air, it is impossible in the case of ultrasonics, but it is possible through the nucleonic instrumentations or radioactive sources. Advantages: it is non-invasive. We have seen that this is non-invasive, or just right now I told it is a non-invasive techniques, right. Particularly useful when other techniques fail. Okay. In many situations we will find that the other techniques will fail, because you see the radioactive sources have some hazards, unlike other sources. If I use any other conventional sources, if you use then radioactive sources also always associated with some hazard. So, unless it is justified, that means you have to use nucleonic instrumentation, nobody will allow you to use the nucleonic sources and detectors. Disadvantages: first of all, with its associated problem of hazards, as I told you. In applications, let us look at density measurement, thickness and level measurement. These are the basic three measurements we will do. That means density of a liquid we can measure, thickness of any surface we can measure, thickness of a coating, suppose wax on a paper, that we can measure. Suppose a very common examples we are telling that we had a strip chart recorders, almost all of you know, and strip chart recorders is used extensively in instrumentations. Okay. It is, even though we can make the data equations, we can store in the computers, but always people want some hard copy also. So, if you want to store that type of signal, suppose I am recording a signals of temperatures over 24 hours time with a sampling of 10 minutes at every 10 minutes, I want to record that signal, that temperature on a strip chart recorder. One of the method is that you use the strip chart recorders with a thermal stylus, where thermal stylus will move and the recording it looks like this. That means, you see that if I have a, let me take a blank page. So, I have a strip, it is moving, right. So, the stylus is coming down here. So, I am getting impression over this one. So, this is in time and this is in temperature, degree centigrade. So, I will get a temperature at any time, what is the temperature of the particular process, that can be viewed from this particular impressions. So, there are ink stylus, ink has a problem because you have to refill every time. So, all these cassettes are also this there, but instead what you can do that this entire strip, entire piece of paper, that means which is rolled, it is unrolled here, it is coming down in these directions. So, what will happen, you see that impressions will, because if this is blackened, this paper or some other color and coated with wax, right, this paper if it is coated with wax, this paper is coated with wax. So, what will happen, you know that it will, once if it is heated, this suppose this stylus is heated, if the stylus is heated, then what will happen, you see this will give an impressions, because the wax will melt up and it will give you the impressions from which I can record the temperatures, right. This is one of the method, I mean one of the applications of the instrument of the strip chart recorder in instrumentations, right. And so, there precisely I have to control the thickness of the wax coating over the paper, right. Uniformly you have to, it should not be very thick, it should, because if it is very thick, then this hot stylus cannot give an impression. If it is very thin, that might be useless to us. So, those precise, I mean precision, I mean coating we have to use, we can use the nucleonic instrumentations method of measurement of the thickness, right. Humidity of grain, this is another method, I mean other examples of the, because in the grain, if there is always, if to store it, I need some particular humidity that is to be maintained for the good preservations of the grain. So, that measurements of humidity in the grain also can be possible through nucleonic instrumentation. Determinations of material composition, okay, true detections. So, what is the material composition, that also can be detected, is possible through nucleonic instrumentation. Leak detection, that means if there is a leak in the pipe and all those things, that can be detected, especially in the underground pipe, it is very difficult to know where the leak is. So, it is possible to record through, it is possible to find through nucleonic instrumentation. Also, determinations of age of archaeological samples, because you see many India is, I mean our is a great country, you will find that in many places the old sculptures, old, I mean things are coming up, I mean there are many sculptures are coming up, right, which might be 2000 years old, might be more than that. So, to know this age of this particular samples, we need some, I mean some sort of radioactive sources and detector technique by which I can tell exactly the age, right. So, there is another application, though it is not much of industrial instrumentation, but this is another applications of nucleonic instrumentations. Now, radiative source or radioactive source. So, this should be actually I should say radioactive source instead of radiative source. These are alpha particles, beta particles, gamma rays and neutrons. There are 4 basic, I mean there are some advantages and disadvantages of this particular method. So, we have alpha particles, we have beta particles, gamma rays and neutrons. Now, alpha particles, it is a high ionization, it will ionize the gas through which it will pass. Low penetrations, only it can pass 10 centimeter in air, and energy is high, that means 10 m electron volts, which is quite high, supposed to be quite high. Beta particles, it is less ionizations property than the alpha particles, its penetration is much higher, 10 meter in air, and its energy is medium energy, so 0.5. So, you can see that its energy is less. Then gamma rays, it is a penetration is several inches of lead, because lead is very difficult to penetrate through lead. Any other alpha beta particles will not penetrate through lead. So, that only the gamma rays can penetrate several inches, but if you use a thicker lead, gamma particles also cannot penetrate through it. Neutrons, neutrons is a different source. It has a no ionization effect, it has large penetrations and a very small, very small energy, 0.025 electron volt. You can see that's how less it is, right. Now, half life, this is a very common form of it's called parameters. Whenever you are using in radioactive sources, you must be aware of this half life period. Sometimes we need shorter half life period, sometimes we need larger half life period. It is a time required by a radioactive material to decay to half of its initial size, right. It is the time required by radioactive material to decay to half of its initial size. Mathematically, it is defined as half life equal to T 1 by 2 equal to 0.693 by lambda, 0.693 by lambda, where lambda is a decay constant. Okay. Now, source materials, what are the different sources of this alpha, beta, gamma rays and neutrons? Let us look at that. We have cesium 137, its half life is extremely small, 30. That is a problem, all of you are aware of the radioactive sources, half life is extremely high. So, it will continuously emit all these rays, which are some of the rays are harmful to the human body. So, obviously, it will ray for 30 years, half life is 30 years. Cobalt 60, half life is 5 years. Then we have americium 241, which is half life is 460 years, extremely high, you can see. Now, detectors, there are different sort of detectors we will use in instrumentations. In this type of instruments, we will slowly detect, we will slowly explain all this one by one. We have gas detectors, okay. Gas will be ionized, that means ionization chamber, because once the gas is ionized, I can say how much the ray is, because if the ray passes through some body, obviously some of the rays will be lost and we will get some rays. So, accordingly I can calculate. Okay. Then the proportional counter, all these are basically gas detectors. Then you have Geiger-Müller counter. Geiger-Müller is basically a German name, so there should be umlaut. I am not writing, so it will look like this. Okay. So, Geiger-Müller counter, right. So, we have a scintillation counter, its principle is slightly different of the gas detectors and scintillation counters. We will discuss all these things in details. We have a solid state detectors, okay. This is basically solid state detectors. We will see what is the PIN junction diodes. We will see that two P and N junction, in between one intrinsic junction will come. So, it will make the solid state detectors. Now, these are characteristics of radiation detectors. You see here, these are characteristics of radiation, size of the pulse and this volts. You will see that different region, which region will be utilized by the which, that will be slowly available to us. The gas chamber operating in the different regions are region 2 ionization chamber, region 3 proportional counter, region 4 Geiger-Müller counter, right. Now, ionization chamber, you see here, the chamber is normally filled with a suitable gas such as argon at atmospheric pressure and sometimes at a higher pressure, right. This is almost, this very inert gas, right. So, the chamber is normally filled with a suitable gas such as argon at atmospheric pressure and sometimes at a higher pressure. An electric field is set up between the electrodes by applying a DC voltage. Right, an electric field is set up between the electrodes by applying a DC voltage. As radiation is incident on the chamber, the gas is ionized, obviously, okay, and the electrons and ions thus formed are attracted towards the respective electrodes, giving us the output current. Okay. Is it clear? Suppose I have we have discussed the ionization gauge, is not it? That in the case of low pressure measurement. So, same basic principle is same actually. You see, look at here, if I have like this one, if I take this pen. So, I have, so gas is ionized, suppose this is I am getting a, suppose so I am putting a meter here, okay, 2 plates. So, the positive ion, suppose positive ion will move this direction, negative ion will move in this direction. Okay. So, resulting some current which will be detected by the ammeter, right. So, how much current I will get, that will be proportional to the ionization, right. The more the gas is ionized, I will get more and more current, and the gas will be more and more ionized if there are more number of particles comes and fall on the chamber. Clear? The length of the plateau in region 2 depends on the nature of the gas inside the chamber and on the specific horizon. Let us go back. Let us, okay, length of the plateau you see here, okay. This is our, so we can go back to our original discussions. So, the length of the plateau is in region 2 depends on the nature of the gas inside the chamber and on the specific ionizations. Okay. So, what type of gas is there, that is one factor, and what is the ionization, specific ionization, both depends on these two. So, length of the plateau will be there. The specific ionations is a number of ions. We have defined the specific ionations. So, what is the specific ionization? Number of ions formed per centimeter of length per atmospheric pressure, right. Number of ions formed per centimeter of length per atmospheric pressure. Proportional counter. Due to larger mobility and the higher acceleration of the primary ions produced secondary ion, this is known as gas multiplication. Okay. Now, you see the when the ions move in a gas chamber, okay, when the ions move in a gas chamber, there are gas molecules, okay, and it will knock out some of the outer electrons of this. So, it will further produce some of ions. Okay. That means a gas, because there is, because you see that we have a plate, is not it, we have discussed. We have plates here. I have positive ions, negative ions, right. I am connecting this battery. Okay. So, these rays are coming here, ionizing the gas. Now, this will move with a very fast acceleration in these directions. So, whenever it is moving, it will may knock out some of the, it may further ionize the gases or the molecules of the gas, right. So, it further ionize, obviously the more and more current I will get, right. So, these are the secondary ions, because this is the primary ions which is due to the incident rays, whereas when these rays will do, when this the ion moves through due to the electric charge, due to electric potentials on the both sides. So, it will produce secondary ions, right. This is known as gas multiplications. The gas amplification factor A of 2 by n is obtained, where n is the number of mean free paths away from the central wire anode, right. The output voltage pulse remains truly proportional to the number of ion pairs initially formed over the first half of the region 3, and the system is used as a proportional counter. Clear? The output voltage pulse remains truly proportional to the number of ions formed, number of ion pairs initially formed over the first half of the region 3, and the system is used as a proportional counter. Now, let us look at the Geiger-Müller counter. Again, I am telling this is should look like this. That means umlaut should be there. Okay. The region 4 is known as the Geiger region, okay, of the characteristics curve of the detector. The property of the counter operated in this region is the appearance of the output pulses which are of the same size independent of the number of ions formed initially by the radiation, right. So, the property of this counter operated in this region is the appearance of the output pulses which are of the same size and independent of the number of ions formed initially by the radiation. Output pulse amplitude may be as high as 100 volt. So, it is quite high, so I do not need any further amplification. They are primarily used for gamma radiations and in some cases for more energetic beta radiation, right, that is you must know. The end-on type counters are also used for counting of alpha and beta rays and soft X-rays which can penetrate thin windows made of mica or mylar, right. In some cases it can penetrate, in some cases it cannot. Let us look at these scintillation counters. Okay, that is figure should be 1. So, okay, this is scintillation incident radiations, scintillation materials. We have photocathode is a photomultiplier. Photomultiplier tube is, please note, it is nothing but it will multiply, because this signal, the current which you will get will be very small, right. Now, function of this photomultiplier, because incident light will fall on this photoconducting material. So, it will give some current, right, because some electron out from will be emit, it will give some current, and the photomultiplier is nothing but it photomultiplier tube, actually it will enhance the current. Okay, there is a immediate multiplications of the current. So, I will get higher output, that is the reason we are calling photomultiplier tube. And incident radiation falls, the energy falls, energy is consumed and in the scintillation material, right. And the scintillation material releases photons, which are in turn detected by the photosensitive cathode of a photomultiplier tube. Okay. Let us read it again. As the incident radiation falls, the energy is consumed in the scintillation material, releases photon, okay, which are in turn detected by the photosensitive cathode or photomultiplier tube. Scintillation material used are for alpha particle zinc sulphide, okay, then for beta and gamma particles sodium iodide and with thallium additive. Anthracite or naphthalene are also used. These are the basic. Now, this is solid state detectors, as I told you. We have a N type and P type regions, and we have a intrinsic semiconductor in between the two. I will get a output, so that will be utilized, because I need a power supply. So, this I will get can be utilized for measurement, right. PIN diodes are used, which are nothing but simple PN diodes with an intrinsic layer. As the radiation falls on the intrinsic layer, electron hole pairs are generated, which move in different directions. Thus, we have an output voltage which is proportional to the incident radiations. PN diodes are used, which are nothing but simple PN diodes with an intrinsic layer. As the radiation falls on the intrinsic layer, electron hole pairs are generated, which move in different directions, two different directions obviously. Thus, we have an output voltage which is proportional to the incident radiation. Clear? Without any incident radiation, so I won't get any output voltage. However, there is always a background thermal noise, and hence they are operated at a cryogenic temperature. Alpha detectors. What are those alpha detectors? Ionization chambers with CH4 as a gas, proportional counter. Beta detectors are, for the beta rays we need to have differential mode sensing, as they are generally radiated with alpha and or gamma rays. You see, we have this is a detector system for beta rays. We have detectors, we have beta which will block beta, so it will gamma, so it will come out of this. So, beta will be blocked, so ultimately detector will come out, or output will get. The output of the above two are compared to get the contributions of the beta rays, okay, because here I am getting only gamma rays. So, I am getting, so these two will be compared, so that I will get only the contributions of the beta rays, right. Now, neutron detectors are slightly different, as you know. In this case, we use the indirect method. So, B10 plus neutron, lithium plus alpha. Use the detectors and thereby detect the neutrons, right. Obviously, will some detectors which will detect the neutrons. Some applications, density or level measurement of liquid in sealed containers, right. In sealed containers, if I cannot see from outside, because in all other conventional methods I must take out a sample and then I can measure the density, but in the nucleonic instrumentation is a non-invasive technique I can use to measure. So, it is for a sealed containers I can measure the density as well as level of the liquid inside the containers. So, we have a test objects, okay. So, I am schematic of density level measurement. So, I am giving a way we are getting outputs. This I am actually this output we are measuring. How? Let us look at I equal to I naught exponential mu into x. This is basic expressions, right? Obviously, what is that? Let us look at I will be I naught will be always higher than I. Okay. So, I equal to I naught exponential minus exponential of mu x, where mu is the absorption coefficient. Now, mu is a function of atomic weight and density, etc. Right? Mu is a function of atomic weight and density, etc. Obviously, that will vary the I will be varied in this case. Please look at, right, this will vary, this I will vary, clear. Hence, depending on the output signal, we can tell the density of the test object. By looking at the output signal, I can look at the density of the test object, because atomic weight, if the density changes, so the atomic weight will change. If the I can change the density. If the density changes, that value of I also will be different, right. So, atomic weight might be same, if the density might be different, but the atomic weight can be the same. For level measurement, you use the following scheme. This is a scheme of the level measurement. So, we have a source, you see here, we have a detector here, okay, and so this is a level measurement using nuclear instrumentation. So, I have a liquid here. So, how it works? Let us look at. When passing through the fluid, the absorptions will be more, and hence the amplifier output forces the stepper motor to move the source and detector to move upward, right. You see what will happen. So, when passing through the liquid, this will, so it will always try to move this stepper motor to move it upward, right. When they reach the interface, the absorption falls, and thus we know that the level is reached. Clear? Let me go it again. So, the basic principle is something like this. These two system, this let me take that means this stepper this source and detector will be initially at the bottom here. Okay. So, it will move up. How it will move? So, it will be detected because they have source and detector. When it will stop, because incident ray and the deflection, this radiated ray and the detected ray will be different, because it will slowly move. Excuse me. We have a stepper motor assembly, so that what will happen, it will slowly move. Now, whenever it will reach the top surface, what will happen? There is a difference of the receiving signal. So, at that time you can immediately stop it and see that what is the level. So, that will tell you the level of the system, right. Clear? So, when passing through the fluid, the absorptions will be more, and hence the amplifier output forces the stepper motor to move source and detector to move upward. So, when through the liquids, I have a large absorptions of the open particles, so that I will get a less output, right, at the detector side, and when they reach the interface, the absorption falls. So, now we know the level has reached. So, now that position can be reflected, position that where movement of the stepper motor can be calibrated in terms of level, because you see, even though I am here, I am showing you, actually in practice, if it is sealed container, you cannot see the inside. So, outside should be calibrated, sorry. So, this outside should be calibrated, that means this should be graduated like this one, because these you cannot see, this all this level even though this. So, whenever this through this one, absorption will be high. So, I will get a difference when the signals. So, whenever it reaches this top surface, that means the top surface of this level, absorption will fall. So, obviously detector output will be different. So, at that time I can stop the motor and I can see this one. This is forcibly when the absorption always it will move up, step by step it will go up, even though it is not very continuous, but it will work, right. So, at this point I can measure it and tell the level of the liquid inside this vessel, which is sealed from outside, so we cannot see it from outside. when they reach the interface, the absorption falls, and thus we know the level is reached. The level is then shown on the display, right. The thickness measurement in rolling mills is very common. Okay, as you see here, nucleonic thickness measurements. So, I have rolling mills, rolls are coming out. These are the basically rolls, which is from the ingots. Okay, from rolling mills, that means I have a roller. Okay, so rolling is the thickness, then it is I am getting a proper shape. I want to measure accordingly how much pressure I will give on the roll, that can be determined. Okay. That means how much pressure I will give on this particular roll, how much pressure it will give on this. Accordingly, if I give more pressure, the thickness will be small, right, thickness will be reduced, whereas if I give less pressure, so the thickness will be large and large. But I have to measure the thickness at every time. It is a continuous measurement, right, so that it will control, and I can give the signal feedback to this roller, so that accordingly pressure will be given on this, and I can control the exact thickness of these devices, exact thickness of the roll sheet which is coming out from the rolling mill in a steel plant, right. Let us look at principles. I have a source and a detector, fine, no problem. We know that again I equal to I naught exponential minus mu x. Thus, the detected signal directly will give us a measure of the thickness. So, that if I have a calibrated output, suppose I have something, I made the calibrations, okay, accordingly I know that for this, suppose a 5 centimeter thickness of the rolling sheet, okay, I know the what will be my value of I if my I naught is constant. So, I will use that principle. So, obviously, if I or continuously I will detect I, which is the other side where I will detect I. You see, I will detect I at the detector, and there is a pre-assigned value of I for this thickness, 5 centimeter thickness, what will be the value of I. If I do not get it, if suppose if it is less, that means thickness is more. Okay. So, I should press this roller, so that the thickness will be of proper size, clear. Thus, the detected signal directly will give us a measure of the thickness, right, which can be utilized to control the thickness of the rolling sheet which is coming out of the hot rolling mill. Now, coating thickness measurement. Coating thickness measurements, I have given example. One of the good example of the coating thickness is that I told you in the strip chart recorder, that strip chart is coated with a wax. So, that type of situations I need to control the thickness, even though it is slightly, it is a fine coating. So, determinations, because whereas in the rolling mill it is quite large, I mean compared to here it is a fraction of a millimeter in the coating, okay, whereas there it is the much higher, it is a multiple integer multiples of the millimeters. Example, wax on paper or plastic or aluminum foil. This is a good example. Wax on paper is a good example, okay, which is used, as I told you, in the strip chart recorder. The above mentioned can be done, above mentioned method which I have discussed can be done in the various way. One of them is the differential beta transmission gauge, as shown next. What is that? Intensity of the detectors will vary according to the coating, and the differential meter gives the required output. Let us look at, okay, fine. I have a coating, which is coating is coming through this one, okay. Let us look at. So, I have a coating, this is a coating of the, I have a source, I have a detector on this side. So, this is actually, suppose this is actually paper on which I am making the wax coating. Suppose this is wax, this is the wax coating. So, the wax is coming through this one and making a coating, right. So, I have a source and detector. So, obviously, this thickness of detector output, okay, you see here. So, there you will get a some, I mean I have a source, I have a detectors, here I have a source also detector. So, it is continuously coming through this one, it is continuously going, this roll is continuously moving in this direction. Then what will happen? You see here. So, the source detector will give you some output. I know some differential, some predetermined differential output I will get, because why we have made like this one, because this thickness will be very small. So, I need some differential arrangement, so that it will, I will get more deflections or more output, right. That is the reason this differential arrangement. You can say that whatever the principles which you have used for the thickness measurement of the rolling sheet can be utilized, but if I utilize that principle, there will chances of lot of error, okay, because the thickness there it is quite high, it is a few, I mean centimeters, whereas here it is few millimeters. So, I need some differential arrangement, okay. I have some output here, and if I get this one, I will get some output. So, obviously, this output will be less than this output. So, this output will be higher and this output will be lower. So, I will get a differential output. Okay. That can be calibrated in terms of the thickness of the coating of the wax. Clear? Now, leak detection in underground pipelines, it is very difficult to, if you have a leak in the underground pipeline, especially in the municipalities, in the cities. So, it is very utilized, but it should be safe at the same time, because if I use radioactive sources, that half life is extremely high, that will be a problem. You see, this is one of the example how you can detect if there is any leak in the pipe. Okay. This is I am taking a section of the pipe. Okay, there is a ground, and this pipe is obviously installed few meters, might be 1 meters, might be half meters below the our earth surface level of the road, right, or the footpath. Now, what is actually the principle? Principle looks like this. Okay, we are using here Geiger-Müller counter. Okay, basically Geiger-Müller counter is used. 2 Geiger-Müller counters we are using to detect the leak in the pipe. How? Let us look at. Inside the inflated rubber ball, we have a sodium 24, which is radioactive. Clear? Inside the rubber ball, let us look at again. Inside the rubber ball, we have a sodium 24, which is radioactive. That means inside the rubber ball, we have a sodium 24. Clear? Fine. Which is radioactive. The signal of this Geiger-Müller counter is maximum at the position 2, that is at the position of the leak. Okay. Okay. Suppose here we have a position 2, this is the position 2. So, signal at the position 2 will be higher because there is a if there is a leak in the pipe, because it is slowly moving. So, leak in the pipe. So, I can detect that way. So, signal of the Geiger-Müller counter is maximum at the position 2, that is at the position of the leak, right. We use 24 sodium as a radioactive material because of the following reasons, because of its half life basically. The pipeline under question may be a water pipeline, hence we need to take account the nucleonic hazards associated with it. So, it should not be very much hazards. So, the hazardous, that is we should look at. 24 sodium, sodium 24 has a half life of 15 hours, right. So, it is very short. So, it dissolves readily in water, making sodium chloride, that means common salt. So, that is a great advantage of this particular sodium, right. So, obviously, if it dissolves and make the common salt, there is no problem, because almost there is always some water is chlorinated for purifications. So, if you use the sodium, so obviously, if there is a leak also of the sodium 24 from the rubber ball, so it will not make any harm to human being. Now, also it is used for the nucleonic instrumentation used for sulfur content, to measure the sulfur content in crude oil. Contents of natural petroleum is carbon and hydrogen, that is the reason, as you know, it is called as a hydrocarbon industry. All petrochemical industry we always call a hydrocarbon industry. If sulfur is present, then the atomic weight of the crude oil will increase, right, because as we say that we have seen that the atomic weight will increase. If atomic weight increases, what will happen? With the increase of atomic weight, the absorption coefficient mu also increases. Okay. What is that equations? We have seen that equations. What is that equation? The equation looks like this: I naught exponential minus mu x, right. So, the increase of atomic weight, this mu absorption coefficients mu also will increase. Obviously, the I will be different, is not it, right? I will be different if you expand it. So, what will happen? It will be a negative term. So, obviously, if the mu increases, what will happen? So, the I will be different. So, by this I can measure the sulfur. Thus, the output I equal to I naught exponential minus mu x will change, giving us a measure of the sulfur content in the crude oil, right. Now, let us discuss little bit of nuclear medicine, as I told you earlier also, because in context of the nuclear instrumentations, we should discuss some amount of nuclear medicine. Nuclear medicine takes into account the radioactive material for the diagnosis of disease and for assessment of the patient, right. It differs from a radiography in the fact that the source of gamma rays is not external, but rather within the patient. That is the difference between the radiography and the nuclear medicine. It also differs in the way that the radioactivity can be attached to the material that are biologically active in the patient. Okay. It is used to image organ function as opposed to simple organ morphology. I am sorry, this will be opposed. This will be opposed. It measures the radioactive distribution inside the patient, which can be either static or changing with time, right. This is a typical example of the sodium iodide scintillation detectors. You see what will happen, we have a gamma rays coming, we have a scintillation crystal sodium iodide, then we have photomultiplier tube, we have a preamplifiers, we have a delay line, then we have a further amplifiers. I am getting a large gain. Obviously, there should be high voltage that we have not drawn. It should be a high voltage section is necessary because photomultiplier tube needs a high voltage to operate. So, I am getting a current and I will get a further amplifiers, and this is a attenuator. So, accordingly I will get a full gain here. Because you see there is a simple pontometric systems which you are using. So, using this I can give a step gain or I can get different gain of the systems. This is a simple attenuator, all the instrumentation people always we know the people who will do like this one, right. Now, original pulse you will see, you look at here, I am sorry. You see this actually how it works, actually this I have shown how the pulse looks like, because I cannot show it here. So, I took the next page, how the pulse, this output after the scintillation crystal coming, the preamplifier output, how it looks like. Let us look at that. You see this original pulse, okay. Now, the reflected pulse is coming like this, and if I can combine these two, I will get this pulse, okay. This pulse is utilized for making the detection, okay. Combining these two pulse, because other will be cancelled out, I will get a pulse like this one. This pulse will be utilized for making the detection and further diagnosis purposes. You see this is a cross sections of the focusing collimator used in the rectilinear scanning system. Now, all the scanning system is basically, any scanning system, whether it is a CT scan or it is your television camera scanning, basically that is a, whenever there is a rectilinear motion, that means the motion of the detector in XY directions. Okay, rectilinear motion means the motion in two directions, XY directions, I will call it a scanning, right. Here is a cross section of the focusing collimator used in the rectilinear scanning system. Is a sensitivity to a point source of radiation expressed as the percentage of the radiations at the focal point, right. You can see here the sodium iodide detector is common to nearly all the instruments using nuclear medicine imaging. It consists of three components: the crystal itself, which scintillates with the blue light in the linear proportion to the energy of the gamma rays losses in it. A photomultiplier tube, it converts this light into a proportional electric signal. The support electronics, it amplifies and shapes the electric signal into a usual form. Simple nuclear medicine procedure do not involve images, but rather consist of simply placing the detector near the surface of the patient's skins and counting the gamma ray flux. This is a very common example, okay, obviously non-invasive. Any process that involves rectilinear motion of the detector is called the scanning, that I told you earlier. A sodium iodide detector must be collimated in a scanning procedure in order to resist its field of view both along the longitudinal axis and the transverse to it. One such arrangement is shown in the figure, right, which you have shown. What is that? See how it is collimated, we have shown here, right. source sensitivity of point source detection of radiation expressed as percentage of radiation at the focal point. A sodium iodide detector must be collimated. Okay. Now, the cross sectional view of the gamma camera. You see we have a lead shield. Lead shields are all side. You see we have a lead shield on all sides. All the sides we have a lead shield. We have a hexagonal array of 19 photomultiplier tubes. Okay, these are photomultiplier tubes. We have a sodium iodide crystals here, glass window through which you can crystal house. You can see the crystal housing. Okay, this is optical guide. Okay, and these are sodium iodide crystals you can see here. Okay, we are getting output signal x plus, y plus, which can be given to like oscilloscope like systems, the horizontal plates and the vertical plates, to get the proper picture. Now, gamma camera, the gamma camera is also known as the Anger camera. It is a stationary imaging system that is simultaneously sensitive to all the radioactivity in a large field of view. It does not depend on the motion of the detector to piece together an image, right. The radiation detector is a single sodium iodide crystals 30 to 40 centimeters in diameters and 1.2 centimeter thick. Okay, this is quite large. You can see the detector, sodium iodide crystals 30 to 40 centimeter in diameter and 1.2 centimeter thick. The detector is viewed simultaneously by an array of photomultiplier tubes arranged in hexagonal fashions at the rear of the detector, as shown in the figure. Okay, just to have the shown, you see, you see when, okay. Detector is viewed simultaneously by an array of photomultiplier tubes arranged in a hexagonal fashion at the rear of the detector. As the gamma ray enters the sodium iodide crystals, the scintillation light spreads and each photomultiplier tube picks up a fraction of this light, right? Clear? So, where the gamma ray enters? Let us go back again. Gamma rays enters through this thing. Okay, we have a sodium iodide crystals, it is scintillating lights, it is going to the photomultiplier tubes, I am getting the electrical output. Clear? As the gamma ray enters the sodium iodide crystals, the scintillation light spreads and each photomultiplier tube picks up a fraction of the light. The fraction of the total light seen by each tube determines the position of the original point of entry of the gamma ray. Clear? Fraction of the total light seen by each tube determines the position of the original point of entry of gamma ray. Now, voltage corresponding to the x, y coordinates of the gamma ray are reconstructed from the signals of the photomultiplier tube. This is done basically by the analog electronic circuit. Now, in the single photon emission computer tomography, it looks like this. SPCT uses a large area scintillation assembly similar to the Anger camera or the gamma camera and rotates it around the patient. Okay, it rotates around the patient. Many of the isotopes used in nuclear medicine produce a single photon or gamma ray in the useful range of the energy. Clear? The collimator is designed to collect the radiation from parallel rays, and these are used in the process of an image reconstruction, which is analogous to the method used in the computed tomography. Multiple planes or slices are reconstructed at the same time, which helps us to show the both information in the volume of interest by constructing several cross-sectional views in addition to this offered by the conventional nuclear camera. Now, positron emission tomography is slightly different. Certain isotopes produce a positron that react with electrons and produces two positrons at 511 kilovolt at opposite directions. Positron emission tomography uses this property to determine the source of radiation. The isotopes have two means of decay. The nucleus can capture an orbital electron that combine with one positive charges. Okay. So, the nucleus can capture one orbital electron that combines with one positive charge. A nucleus can emit a positive charge in the form of a positron that combines with the external electron, right. So, there is a two method by which you can method of decay of the isotopes. Obviously, all the radioactive materials basically is decaying, that you must know. The combinations of negative and positive particle annihilates the charges, and the masses of each energy and momentum are conserved and the two 511 kilovolt gamma rays are emitted in the opposite direction. The property of the simultaneous emission of the gamma rays in opposite direction gives the positron emission tomography and the ability to locate the region of origin, right. So, that is necessary, you must know the origin. Instead of multi-hole collimator as in most of the gamma cameras, two imaging detectors capable of determining XY positions are used, right. And each XY pair is accepted if the two scintillation effects are coincident and have energy levels close to the expected value of the 511 kilo electron volt. The simplest PET uses two modified Anger cameras placed in the opposite side of the patient as shown in the following figure. Okay. So, you can see this is a paired camera, okay, how the is rotating. Okay. So, that continuous, so it is rotating in these directions. Okay. So, rotating in these directions. So, the patient will be covered by two Anger camera. And please note that in the new clinic instrumentation, so the hazard is a great problem. So, you have to think of all this whenever you are using what type of radioactive materials you are using. Though the half life and all this thing is not that large, but the amount of rays you have to think of. So, the proper hazards, and it's sometimes there is environmentalists are there. So, until unless you can manage with some other instrumentation which is non-hazardous like ultrasonics and any conventional instrumentation of level gauge or density measurement that is to be used. But in some situations, as I told you, like the detections of the leak in the pipe underground, or suppose in a closed containers, I want to know the level of the liquids and all this thing. It's very difficult to know, especially it is sealed. The container might be closed, it does not matter, because if I have a inside electronics already installed inside, so I can sensor installed inside, I can detect. But if it is a separate container, suppose a cylindrical drum, I want to know how much the liquid contains, which you cannot see from outside. For that type of situations, I can use this type of radiation technique or technique. Okay. So, this is to be basically, all of you have to be careful. That means that I told you several times. That means if I can manage with other instrumentation systems, conventional non-hazardous systems, we are not supposed to use radioactive sources, right. So, with this I come to the end of this lesson 26. Welcome to the lesson 27 of industrial instrumentation. In this particular lesson, we will study basically the measurement of magnetic field. Basically, two sensors we will consider here. Though the title of the lesson is measurement of magnetic field, but you will find that especially the sensor, the second sensors which we had. So, we will study the measurement of current, measurement of power, all those things. But the first sensors, that is the search coil, is basically used for measurement of magnetic field, and second one is the Hall effect transducers that can be used for measurement of magnetic field as well as current. In fact, you will find that this particular sensors is extensively utilized, though it is named that it is used for the measurement of magnetic field, but you will find that it is extensively used for the measurement of current, especially high current, as well as the measurement of position or the proximity sensor, measurement of power, multiplications of the two signals. These all those things we will see that what are the different application areas of these Hall effect transducers. Let us look at the contents and all those things. contents are search coil. Magnetometer search coil we will basically discuss here. So, magnetometer search coil looks like this, that you have a, as we know that if a magnetic field, that if you move some coil anywhere, some voltage will be developed. So, using that principles that voltage will be measured and that voltage will be calibrated in terms of the magnetic field, right. If the other things remains constant, obviously we will find that the output voltage will be directly proportional to the magnetic field. So, that is the search coil or magnetometer search coil. Sometimes people call magnetometer search coil, sometimes we call it simple search coil, right. And second transducers we will consider in details is the Hall effect transducers as a I mean many times amplified or something like that. That means I will apply a magnetic field which is coming through this, going out this, right. I am applying a current, electric current which is entering through this and going out of this. That means I have applied some voltages, that is the reason that some current is flowing. If I apply a voltage, a magnetic field here, you will find that across these two surfaces, this and this, a potential will be developed. That potential is actually, we are calling it a Hall coefficient, right. Let us look at that problem again. This is our problem. So, given Hall coefficient for the germanium crystal is -8 × 10⁻³ volt meter ampere Weber per meter square. Solutions E h equal to kh Bi by T, we have seen. So, B equal to kh T by kh by into I. So, this you just put all this value of B. Okay. So, B equal to 0.012 Weber per meter square. So, now when the Hall field and Lorentz force must balance. So, I can write it is the movement of the velocity, B is the velocity of the electrons inside the Hall sensors. So, E B h by B. So, B equal to E h by B by small b. Let me go, yes. So, which will give you the speed of the electrons as 972, these are all the dimensions of the Hall plates, B is the dimension of the Hall plates, 9722 meter per second, right. With this I come to the end of the lesson 27 of industrial instrumentation.